In this lesson, we're going to get a much better understanding, I think, for a not only a conceptual feel for center of mass, but how the mathematical definition meets up with that conceptual notion to really make a lot of sense. So what I want you to consider here, and you'll need to draw some of this in on your notes, is a two-particle system, so a 25 kilogram mass and a 75 kilogram mass, making up a two-particle system. And what I want you to do is put in a line, which is going to represent a really light, really strong bar that's going to connect these two pieces together. So there's going to be a center of mass point where that's my seesaw point, right? And we're going to say, well, where's that seesaw point? Where would it perfectly balance? Well, the bar itself we're giving no mass to, so that's negligible mass by comparison to the 25 and the 75. So we only have x-axis to work here, and m1 is at position vector x1, m2 is at position vector x2 divided by the total mass. Now, please make sure you get this into your notes. It's really important that you put in here that you must use the positives or negatives that go with the x's to get the correct answer. Now, here it's on the positive x-axis, so it's not an issue, but we have mass 1 is going to sit at position 2, mass 2, 75, sits at position 12, and then there's a total mass of 100. So we plug in, it's just a calculation, there's not really a lot of analysis. 9.5 represents the seesaw wedge point where we would be in perfect balance. Okay. Now, to get a better feel for what center of mass is, the calculation is doing mathematically, let's just break up our algebra a little bit here. So what I'm going to do is split apart. Let me erase here. I'm going to take the total mass and leave it as 100 beneath just the 25 and the 75 and think of it as two separate calculations. So I guess the first thing I would like you to do is make sure that you understand mathematically that this equality can become this equality and that it's mathematically valid to do that. You'll get the same answer. When we do that, we can see what the significance is of the calculation we're making mathematically. The 25 divided by 100, as it shows here, is 0.25, and the 75 divided by 100 is the 0.75, and we're multiplying that by the position vector. So essentially, what we are doing is saying, how important is this position 2? Well, mathematically, how important it is, it's 0.25 important. How important is the position 12? Well, that's 0.75 important. So by weighted position vector, I mean mathematically weighted, like a weighting of importance. So when we do that, we then get the center of mass point mathematically, but I think understanding this center of mass position vector calculation as a summation of weighted position vectors will help us out to better understand what the calculation is actually doing and why it works. Well, that's in one dimension. So on our next page here, I have a two-dimensional example. So we'll get to the answer in a moment. But again, draw in those really light, really strong rods. So what I want to think of is what would happen if we had particle M1, M2, M3 making this like little triangle-shaped object where all the mass is in M1, M2, and M3, and we're connecting them with these really light, really strong rods. Well, here we have a two-dimensional example, and you are going to make the same calculation that we just made individually, separately, first in X and then in Y. So here I have the X shown. So particle 1, let's do that in red, is a 10 kilogram particle at X position 3. M2 is a 6 kilogram particle at position 7, and M3 is a 12 kilogram particle at position 10. So that is what I have shown here. And we get the x coordinate for the center of mass is going to be positive 6.9, so almost 7. We do the same thing in the y direction. So we have the 10 kilogram mass, M1 sitting at y position 4. We have the 6 kilogram mass sitting at y position 6. And we have the 12 kilogram mass sitting at y position 3. When we divide by the total mass, we will get a y position of 4. And we see that we have the center of mass point is now at 6.9 and 4. So the center of mass point is here. That's a very interesting result, because remember we said that was nature's balance point, but that is not on the object at all, and that is correct. The center of mass point of an object does not have to be on the object. Whoa! How does that work? Well, we said it was nature's balance point, and I think the easiest way to see it is to think of a hula hoop or a circle. If we take a just a circle-shaped object, like a hoop, a wheel, a disc, right? Think of the hula hoop. It's not the greatest circle, but think of it as a perfect circle. If you wanted to balance it, if you held the hula hoop vertically, you would be right underneath the center of mass point. And you could balance it there. You'd have to be pretty careful about how you balance it, but that's how you would balance it. Well, if you turned that hula hoop on its side, right? Now the center of mass point is still in the center. I would have to glue a light bar, and then I could put my wedge right at the center, and that would balance it as well. So the center of mass point does not have to, and is often not on the object itself, depending on the shape of the object. So keep that in mind, and as always, make the calculation that you make and have confidence in the calculation. If you don't seem to understand the answer, then we would have to reconcile why it is that our math is giving us that answer, or look for a mistake in the mathematics. So you'll have some calculations to make on these types of problems, and we'll begin our problem solving, and we'll go on from here.